Welcome back. So the next video is going to be about reconstructing the example dataset for X-ray epipolar consistency and also doing volume rendering. This repository comes with an example data directory right here that contains both the synthetic pumpkin dataset and this walnut raw data. Now this is not data that I am providing. You will have to download it from Zendu from this link. It's going to be like a bunch of zip files that you have to all decompress and a txt file which gives you the geometry. I've already done this for you. Now let me show you. This is the directory, and right here we have the images. This is just the uncompressed zip files essentially. And here's the txt file that gives you the source distance, the source detector distance, and the source. Okay, this now has the source offset and the distance offset sample. So basically, to get the source isocenter distance, you'd have to add the two together. That would be 210 roughly. And it also has the pixel size, which is pixel spacing for me, which is 0.05 millimeters. Right. Now we're going to reconstruct it. I have already cloned the repository right here and right here. I also installed already, but I'm not going to show you how to do that. The instructions are in the README. I'm now going to pop up the reconstruction GUI again, but this time I'm going to call define reconstruction job. I'm going to go to the example data directory where I have the walnut data, and I'm going to save this reconstruction JSON in this directory. Now, this dialog is basically for defining projection images and trajectory. First of all, selecting the images is pretty straightforward, except we have to be a little bit careful. This has 721 views, right? And we only want 720 of those because the first and the last ones are identical. Next, we have to supply the right values to SID and STD, which are given in this text file. So again, this is 553 and 74 and 21066, and the pixel size is 0.05. Right. Finally, there's one little thing that we have to be careful about. This is a clockwise rotation. It doesn't actually say this in the file, but I already tried it for you, so I know. And I'm just gonna do done, and it's gonna bring me to the reconstruction GUI. Now this is the trajectory that we just defined. You can see the sample is a lot smaller than what we're used to from the example data. The source trajectory is smaller than the detector's trajectory, which is actually the normal case, and everything is rotating just fine. It has already set up a default reconstruction volume, and the last thing that we have to do is we have to convert to line integrals to make this work. I'm also going to select downsampling, skip 4 and 0.25. That's really just to make it fast, so the reconstruction doesn't take very long for this video. And finally, the reconstruction volume is currently estimated at 2,200 pixels because the projections are pretty small, pretty big. I think we can downscale this by a factor of 0.25, end up with roughly 500 pixels in each dimension. Right, so that's all there is to do, and I would like the cylinder to be cut out, and I'm actually adding a little bit of slack here so that we have fewer artifacts on the border. This is really just for visualization. Since I've already installed the X-ray epipolar consistency package, you can see there's a new button here. That's ECC calibration correction, and that's what we're going to be using in the next video. But first of all, let's try and reconstruct this. I've already tested it, so I'm going to replace the existing file, and now this is the reconstruction again. I hope it's going to be fast, and there you go. So here is a walnut. Now this is a pretty low res image, so it's kind of hard to see, but if we do better reconstruction later, you will see that this one isn't very perfect. You can maybe guess that there are some double edges around that area here, and also in some other places there are just blurrings and double edges. But let's be happy with this for the moment. You can see there's a new button here as well. That's volume rendering. And this one I can click and it brings me to a simple volume rendering GUI. That's this one. I don't care about the overlay, so this is the 3D reconstruction we just did in a digitally reconstructed radiograph. We can also extract an ISO surface, adjust the ISO value. So this is the surface of the walnut. You can see it had a lot of artifacts, so it's not a very good reconstruction. And yet we can do a emission absorption rendering. There's a transfer function option here where you can set it up to look kind of like an actual walnut if you're into it. There you go. Load walnut. This is just a preset. Oh, I guess because of the strong reconstruction artifacts, this doesn't actually look very good. You can also add shading if you want. Okay, I guess we're going to have to do this again later if the volume is better. Reconstruction. Okay, so we're happy with this. I can close this. Now the next thing I'm going to do is actually I'm going to load the existing reconstruction from the directory I just saved it to, and I'm going to export it as a subsampled dataset. So in this case I'm going to go down to 360 images of 1000 by 1000 roughly, and this is going to be good enough to get a decent reconstruction and still be sort of fast. And I'm just going to store this to my desktop, to the install test, which is where I'm working, and I'm going to call a new directory walnut skip 2 2x2. And I'm going to choose this as my output. Now it just downsizes all the images and produces new reconstruction JSON and also OMPL files which are matching the new images. And when it's done, it's going to ask me to load them, which we are. And there we go. You can see now we have image 1, image 3, image 5, and so on and so forth. So it's half the number of images, and the voxel volume, everything is still the same. And we're gonna have to go down to no subsampling, no downsampling here, because we already downsampled the raw data. Everything else stays pretty much the same. Now, if I click again, save and reconstruct, this is a bit slower because now it's more projections. Also, the reconstruction is going to be a bit slower. And here we go with a slightly better reconstruction. But you can see there's quite a bit of dejust still happening in many places of this walnut. You can see double edges here, down here, pretty much everywhere a little bit. And this is what we would like to correct. Now, follow me for the next video.